Which one of these models would be best to predict the population of bison in Yellowstone? What are the uses for the other models? And more importantly, how are these models created? To start making any model, it's useful to first define exactly what we want our model to produce. For this model, we want to have a function that takes some inputs and then produces the population over time. Let's represent this model with this diagram. This box will represent the population. Coming in from the left will be the ways that the population increases. Exiting the box on the right will be the ways the population decreases. Pause the video here and think what arrows need to exist. For modeling population, there is a fairly clear list of how the model can be changed. Population increases when new members of the population are born or migrate into the population. Population decreases when members of the population die or move out. Now for the difficult task in modeling, determining how these processes interact with each other to determine the population. This process requires us to make assumptions, which may or may not be true. These assumptions simplify the problem, allowing for equations to accurately model the new problem. The famous saying is that all models are wrong, but some are useful. Determining what assumptions are useful is an art and requires much consideration. For our first model for population, let's assume that population increases at a rate directly proportional to the current population. In other words, each member of the population is equally likely to have a child at any time. Differential equations are very useful to detail this problem. This is the equation for our current assumptions. This is a representation of how the population will change over time given different initial conditions. For this model, the only initial conditions we have is the proportionality constant and the initial population. Now we can see how the population changes over time. Suppose we start with exactly 100 rabbits and we know that after 1 month we have 110 rabbits. Using those numbers, we can solve for constants and see this graph. What are some problems with this model? The most obvious issue is likely that the population grows unbounded. For instance, after 14 years, there are over 10,000 rabbits. Obviously impossible. Another less obvious issue is that for many populations, growth is not constant throughout the year. For example, large herd animals have a season when most of the young animals are born. How might you solve these problems? We will first solve the problem of birthing seasons. A possible way to account for this is by having the population increase only on certain intervals, instead of constantly. This yields the recursive function that defines the population at the next month based on the previous month. The corresponding graph is, the x-length step on this graph is the season length. Following this is the equation. Now this graph could be more useful to model certain animal populations. This model can be expanded to predict age distributions inside of a population. For more information, see the article on Leslie matrices in the description. This model still has the issue that the population grows unchecked. How can we solve that problem for this in the previous model? To solve this problem, we make another assumption. Suppose that the population has a maximum size k and that the growth of the population is proportional to the distance from k. In other words, when far away from the maximum, the population grows unchecked, like in the previous model. But as it approaches the carrying capacity, the growth slows. Here's the equation. To see how the parameters change this model, examine these various graphs. As you can see, a higher growth rate leads to the population reaching the carrying capacity faster, while higher carrying capacity allows for a larger maximum population. Now for the next challenge. How would you model two populations where one is eating the other? For this problem, we will modify our original diagram to have two boxes, one for the prey population and one for the predator population. Both these boxes will have the same adders and subtractors as before. But since the predator and prey populations impact each other, our model needs to have interaction between the two boxes. We'll make some more assumptions here to model this. First, more prey leads to more predators. And second, more predators leads to less prey. To now turn these models into equations, we'll make some further assumptions. Populations increase proportional to its in size. Prey are killed at a rate proportional to both their population size and the predator's population size. Predators reproduce at a rate proportional to both their population size and the prey population size. And finally, predators die at a rate proportional to their size. Some of these assumptions seem fairly obvious. For instance, it seems clear that if there are more predators, then there will be more predator deaths. Others are less obvious. For instance, why would an increase in the prey population lead to more prey being killed by the predators? Well, imagine trying to catch a fish in a lake with only one trout. That would be much more difficult than fishing in a lake filled completely with trout. Hopefully that helps you understand why the increase in prey population leads to more prey dying. These assumptions yield the following equations. These are called the Lotka-Volterra equations and have no explicit solution, unlike the previous equations. Using a numeric approximation, the graph looks like this. This clearly shows how the predator and prey populations oscillate over time. This is because as the population of the prey rises, the population of the predators also rise. But once there are too many predators, they overeat the prey, causing both the prey and predator populations to fall. While this model is not very accurate at predicting exact populations, it is useful for the information it gives us about the trends in the population, such as these oscillations. For the next model, we will look at disease spread. We will try to model what percentage of people have had, and don't have the disease. We will call these populations the susceptible population, the infectious population, and the removed population, respectively. These three populations are distinct groups of the whole population. How will changing one of these groups affect the other populations? It seems fairly obvious that an increase in the infectious population must mean a decrease in the susceptible population as they become infected. Similarly, an increase in the removed population means a decrease in the infectious population as they become healthy and immune or die. We will make an assumption for simplicity that people cannot be reinfected. This means that the susceptible population will never grow and that the removed population will never decrease. Connecting the arrows in a diagram yields. Now let's make some more assumptions. First, every person exposed to a disease is equally likely to contract it. Second, the size of our population isn't growing. Third, the increase in the number of infected individuals is proportional to the infected population and the susceptible population. 4, the susceptible population decreases at the same rate the infected population increases. 5, the infected population decreases at a rate proportional to the population. And finally, the removed population increases at the same rate. These assumptions yield these equations. The equations here describe the susceptible, infected, and recovered model of disease spread. They're useful for seeing how long waves of a disease are and for seeing how changes in public policy can affect the outcome of the disease. For instance, let's suppose that the government implements a masking policy that reduces the rate of transmission, or the disease becomes more infectious. Then the graph could change like this. While this model is useful, the assumptions we have made it partially inaccurate. Certain diseases, for example, have short periods of immunity and reinfect people. Other diseases affect different age ranges vastly differently, meaning that the assumption that everyone is equally likely to be infected is false. Still, these models are useful because of the large amount of diseases that can be accurately modeled with them. Further, the constants can be found fairly easily through experimentation. Now that we've explored these different models and how they are built, let's take a step back and consider what we've learned about the process of modeling itself. Consider the assumptions we have made to create these models. These assumptions allow us to have models at the cost of oversimplification. Further, by changing these assumptions, we can make more complicated and more accurate models. These assumptions also allow for currently available data to be used. Some numbers we would like to have in our models just can't be measured easily. All of this allows for models to exist which provide a powerful tool to predict the future. As a final challenge, try to create a model that predicts how much caffeine will be left in a person's bloodstream over time. What assumptions will you have to make? Leave your models in the comments below, and thank you for watching.